Hello, and thank you for joining me in this course, Getting Started with Modern JavaScript. I'm Peter Kellner, and my job here is to do more than simply teach you the JavaScript language, but to also have some fun while building a compelling app. By the end of this course, if you choose to code along with me, you'll have built the JavaScript app that drives all of our planets around the Sun, as well as some moons around Earth and Mars. If along the way you want to reach out to me for any reason, feel free to contact me at my blog, peterkellner.net/contact. JavaScript is a first-class programming language first created by a company called Netscape about 25 years ago. Its purpose was to facilitate programming, both displaying and managing user interactions on a web browser. Its beginnings were very straightforward with a limited set of goals. Since then, the language has become vastly expanded, and without any exaggeration, it is the most popular computer programming language in the world. That's according to the latest Stack Overflow survey. Because it runs in practically every computer browser in the world, it undoubtedly has the most runtime of any computer language. On top of all that, I would claim that a computer language is only as good as the APIs that can connect to it. JavaScript was designed from the ground up to communicate directly with the browser DOM, which means it does an awesome job of controlling everything the browser user does. That's all the way from security management to advanced animations in our browsers. Another important thing to mention about JavaScript is that not only is it the language of the internet browser, but it also runs very well inside servers, including servers hosted by the big cloud providers like Amazon and Microsoft. The most commonly used implementation of JavaScript running in servers is by using Node.js and the huge number of libraries written specifically to integrate with JavaScript on servers. Bottom line, JavaScript is a great language. It's absolutely first class, and if you do any kind of development on the web, it's something you definitely should know. This course is titled Getting Started because it's targeted to people who have not used JavaScript or have used it very little. It does, however, assume that you, the student, have programmed at least an advanced beginner level in some other modern computer language. Java, C#, C++, Python, Ruby, pretty much any of the other languages that use similar constructs to JavaScript. I realize saying advanced beginner in some other language is kind of vague, so let me explain a little better with some examples of what I'm expecting you to be comfortable with. I'm thinking that the major features of most languages are these. I expect that when you see a statement like var I equals 1 or const name equals Peter, that you recognize that as a variable or a label of sorts. That is, you recognize it as it's a variable in a language that holds some value that you can do things with, like add, subtract, pass to functions, etc. I don't expect you to know how to use it in JavaScript, but I do expect you recognize that it's a variable. For arrays, I expect that you basically know what an array is, and when you see a statement that looks like this, var mylist equals 1, 2, 3, 4, 5, that somehow this is a variable that holds a list. Regarding looping, I expect you to have the idea that you don't have to repeat lines of code over and over again, and there's constructs that let you iterate or loop through values like array values. For functions, I expect that you get the idea that somehow you can write routines or subroutines that you can call that will do something and, using passed-in parameters of some kind, return a new calculated value. I don't expect you to be able to create these functions without taking this course, but I expect you to know that they basically exist somehow. Lastly, and certainly not inclusive of everything you should know, I expect that you basically understand what a conditional is. That is, you have some way to say if some value is less than or greater than some other value, then do something else. Basically, if you've used these kind of constructs in some other language, you are good to go to take this course. If you haven't, feel free to try to follow along. I suspect you'll do just fine, but you may want to take a more basic programming course before you take this one. Just like with any programming language, you can write the code in a text editor, even like Notepad or TextEdit, and the code will run fine. However, all of us developers have gotten really used to using high-quality code editors or IDEs to develop our apps with. When I'm building JavaScript apps for myself or for customers, I always use an IDE called WebStorm from JetBrains, but it actually has a license fee. But for me personally, I find the extra features I get, especially in JavaScript, are totally worth it. In this course, we're going to use Visual Studio Code, primarily because it's free and it's pretty darn good. We're here on the visualstudio.com homepage, and this is where you can download Visual Studio Code from, whether you're running on Windows, Mac, or Linux. I'm going to assume you've installed this on your computer system. Then we'll go on from there, assuming you have Visual Studio Code set up, and we'll create our first JavaScript app that runs in a browser launched from Visual Studio Code. There's an excellent extension for Visual Studio called Go Live, which we'll install, which will make it really easy for us to develop JavaScript apps that run with a browser web page. I'm assuming you've now installed Visual Studio Code on your system and possibly even gone through a tutorial or two that I'm sure it suggested to you when you installed it, so you have some idea how to use the editor. For our purposes, we want to open a new Visual Studio Code folder in an empty directory. I'm going to click on the Explorer icon, then I'm going to say Open Folder, and I'm going to browse to code on my system, which is an empty folder. Say OK. Now expand the Explorer icon again, and since I'm in Visual Studio Code and I have no files, I essentially want to create one file right now because this is going to be an HTML web page, and I want to call it index.html. That's basically the home page for any website that you browse to. We're going to do this in a development server that we'll set up locally on our computer, but we're too going to call it index.html. I could create this HTML file manually by typing in things like HTML, etc. Or because there's a shortcut built into Visual Studio Code, all I have to do is press the exclamation point and then tab, and it knows it's an HTML file, and it creates the default HTML for me. Now that I have this HTML, I want to set up a local test server so I can run it and see what it renders. To do that, we go into the extensions and we type live server. That's the server we're going to use to display our HTML page. So I'm going to click on live server and I'm going to say install, and that's basically all it takes. Now I can close this page. I'm back on my index.html. If you look on the very bottom right of my screen, you see a button that says Go Live. If I click on Go Live, it says Starting. And now, if I switch to a running web browser, it automatically went to localhost 5500 and nothing showed up on the page. Let's fix that. If I go back to Visual Studio Code, in the body of our HTML, let's put an h1 tag. That's an HTML tag that says make this the main header, and I'm going to call it Solar System App. Now going back to our browser, it automatically refreshed and put the header Solar System App on the page. So now let's create some JavaScript. We go back to our Visual Studio Code Explorer. We press the plus key for new file, and I'm going to want to put it in a source directory, src, because I like to include my code in a folder. So I'm going to say source/app.js. When I press enter, I now have an empty JavaScript file. So for now, all I'm going to do in this JavaScript is type console.log. I'm going to say hello from Peter. So now I have a standalone JavaScript file, but it's not integrated into my index.html or my web page yet. So let's include that in my web page. We go back to index.html, and I like to include my JavaScript in the head tag. So all we have to do is add to the bottom of the head element a script element, which is just script, and then we say source equals, and then the folder source/app.js. And we close it, we automatically get the closing tag. Now, when I save this, browse back to our browser, and we don't see anything different. Well, that's because we did a console.log, which is kind of a debugging thing. So if we want to see that debugger, we click the three dots in the upper right, then we go down to More Tools, click on Developer Tools, and now in our console at the bottom, we have Hello from Peter because our JavaScript actually ran. The source code for all the modules and clips in this course can be found in GitHub. They're in the repository Course Beginning JavaScript separated by dashes. The way the repository is organized, for each module, for example, M3, you'll see a separate folder for each clip. If I were to drill down into the clip 60 drawOrbit, you can see we have an index.html that's basically the same index.html we created a few minutes ago when we set up Visual Studio. But then in the source folder, app.js has a lot more code in it because by this point we've been working on building JavaScript and using our knowledge to create planets rotating around a sun. If you know GitHub and Git well, definitely clone this repo, make changes to it, test, compare differences, do all the great things you can do with Git. But if you don't know GitHub, all you have to do is go to the root of the project folder. That's just this URL, pkellner/course beginning JavaScript. Browse to the code button, go to the bottom and say download zip file, and you'll get a nice zip file you can expand that has all the source code for this course. One more shortcut that I only learned about recently, when you're in the GitHub repo, you can simply press the period button and it will take you right into a web editor inside that project, and you can easily browse all the files in the repo. It's very nice. Unfortunately, you can't run the files from here without downloading them into Visual Studio, but this is an awesome way just to review the projects. When I build courses, I spend a lot of time trying to figure out a demo that I can build that's both interesting and demonstrates many of the features, if not all of the features, I want to teach in the course. The demo that I came up with for this course is a solar system with planets rotating around it and moons rotating around those planets. Let's open that final project, clicking on the VS Code Explorer, opening the folder, heading to the last clip of the last module in the course, that's M7 clip 100, opening that. You can see we've kept the exact same file structure that we created a few minutes ago. See, there's our source/app.js, but now in our source directory, we have a lot more files. It does run exactly the same though. I can click Go Live, that launches our server, and our app automatically refreshes and starts running. Notice that we have our planets running around the sun, and notice around Earth and Mars, we have moons just zipping around as they should be. If you want to look ahead, you can look at some of these files and be confident by the end of this course, you will have developed this JavaScript that rotates our planets around our sun And while those planets are rotating around the sun, moons around the planets. Before doing any JavaScript programming, you really need to understand some basic fundamentals. That includes the language variables, how to declare them, or maybe not, how to work with JavaScript objects, which also includes arrays, and also functions, which are at the core of pretty much all JavaScript functions. Just like every other programming language I know, JavaScript has variables. I'm assuming you've used at least one programming language, and when I say variables, you basically know what I mean. Some programming languages, like BASIC for example, don't require you to declare your variables. You can just use them directly without any kind of declaration. Turns out JavaScript also lets you do that, but it's a really bad idea. I don't know of any case where just using a variable without first declaring it makes any sense. It is a great way, though, to introduce bugs into your programs, so I strongly recommend to always declare your variables. So how do you declare a variable? It's simple. Let's go back to our running JavaScript app we built in the last module. I could add one named myCount here to our app.js JavaScript file we created in the previous module of this course, but there is an easier way for me to demonstrate using JavaScript variables. I have not mentioned that JavaScript is an interpreted language. We write our code, we run our code, and it just works. That does, however, mean that we can type JavaScript into a command prompt, basically a JavaScript interpreter command prompt, and we'll get some results. Conveniently, in our browser debugger, we can bring up what we call a console window, and into that we can type JavaScript commands or statements. Let's do that. To start, in the browser, go to the three dots in the upper right-hand corner, click Tools, then Developer Tools, and that brings up the Chrome debug tools at the bottom of our web browser. Click on the Console tab, and then the greater than sign showing is our prompt to type JavaScript lines of code. Let's get back to talking about JavaScript variables now. We can declare variables in three ways. We could say, let myCount equals 100, or we could say const myCount equals 100, or even though I hesitate to show you this, we could say var myCount equals 100. It's probably easiest to say var because var feels like a shortcut for variable, but don't do it. It's an old syntax, and if you use it, people will think you are old. Use either let or const. The reason is that by saying let, you are declaring that you plan on updating that variable with a new value later on in the code. If you say const, you are saying that this variable will never change, and further, you are declaring that if your code does try to change it, you expect an error to happen. There is never a reason why you should use var in place of let or const. Using let or const is just good coding practice. Let's execute some code now to show let and const doing what we expect them to do. Start with let myCount equals 100, press enter, and it worked. Notice though, we get a message that says undefined. Don't be concerned about that undefined message. We'll talk about this later when we get to functions, but basically everything we typed into the JavaScript command prompt is thought of as running a function, and to be helpful, okay, maybe not that helpful, the command line program is telling us that let myCount equals 100 did not return anything. The value was set as there was no error, but the program that set the value did not return any additional information, hence undefined. Let's now update the value. Type myCount equals 101, press enter, the value updates. We know that because, for some reason, the JavaScript interpreter decided to show us the new value. We didn't actually ask for that, but it did show it to us anyway. To be sure, we can call the built-in JavaScript function console.log, then pass as a single parameter to it our variable name myCount, outcomes 101, then our annoying but harmless undefined message. I do realize I just talked about console.log being a function call, and passed it the variable as a parameter, but I've not told you about functions or parameters yet. Don't worry, I'll get to defining those things later. For now, just assume that if we want to look at a variable, we just type console.log, then in parens we put the variable name and press enter. Let's talk about declaring a variable with const instead of let, making it read-only. Type const myCount equals 100, press enter. Uh-oh, we got an error. Uncaught syntax. Identifier myCount has already been defined. I guess I don't need to explain that. You just can't redeclare the same variable in the same program. Actually, the real rule is that you can't redeclare a variable in the same scope. But since we haven't talked about scope yet, you have to take my word for this, and we'll get back to it later. So for the sake of our practice, let's create a new variable with the new name const myCountData equals 100. Press enter, and that worked. Now say myCountData equals 101, and we get an error saying can't assign to a constant variable, and that's exactly what we would have expected. If you want to try var on your own, go ahead. I can tell you it works like let, but I'm definitely not going to show you since I don't want you to think that I'm old. Back in the old days, that is when I learned to program, naming variables was easy. They all had two characters. The first was a letter, the second a number, and the letter always was uppercase. A1 or Z9, for example. Well, life's gotten a lot more complicated, but that's a good thing. You can still use two-character variables, but in general that's not a good idea. Giving variables longer names doesn't slow your program down, and it's helpful to give meaningful names to variables, so when you look at your code, you get some idea, at least, of what it was meant to do. There are lots of conventions people use for naming variables, some more standard than others, but in this course, we're not going to go too crazy with naming conventions. Let's just stick to trying to use camel case for our names, meaning that they will start with a lowercase letter, then each word in the variable begins with an uppercase letter. For example, if I wanted to declare and initialize a variable named camel case, it would be this. Just let camel case equals 100. The thinking is a camel kind of looks like this, with the hump starting with the word camel. The analogy kind of falls apart with longer variable names, which, by the way, I use a lot. Say, for example, in the app we plan on building by the end of this course, we want to set the number of planets in our solar system to 8, trying not to insult Pluto, of course. You could just say let max equals 8 and be done with it, but no, not me. I'd do something like, say, let max number of planets in solar system equal 8. I once had a very young and smart programmer working for me who complained about long variable names. I ignored him. If anyone complains to you, I recommend doing the same. Long variable names are totally cool in every way. The only issue I see with long names is our camel analogy falls apart. I've never seen a 6-humped camel. So, are you completely free to name variables anything you want? Well, no. There are some rules for creating JavaScript variable names. The most important one is that you can't use reserved words. Those are things like const, let, float, do, and a bunch of others. Here's a URL and a page full of them to avoid. Over time, in JavaScript language releases, some have been added, some removed, but if you follow my advice and use fully descriptive names, you'll be good to go. Another rule is that variables can't start with a number. That's not hard to remember. And yet another is they can't contain hyphens or spaces. They can, however, contain the underscore character, which you'll see a lot in other people's code, just not mine, since I'm a camel case guy. Something also to keep in mind is that JavaScript is case sensitive. That means that if you declare a variable named max number of planets in our solar system, in all uppercase, that would be totally separate from the camel case name, and you'd have two separate variables. You'd get no warning about this if you made a mistake, but sadly there is a default behavior which is likely the misspelled one or the not correct cased one, would become a global variable, more about that later, and something bad would happen when your program runs. It's always hard to teach new programming things because explaining often requires referring to something you haven't explained yet, and if you try and explain, you find yourself referring to the original thing. Kind of a circular reference problem. What am I talking about? Earlier, I wanted to start out the discussion about variables by saying that we will be talking about primitive or value type variables, but since I had not even said what a variable was, that would have been really confusing. Now that we know what variables are, let's talk more specifically about primitive types. MyCount and MyCountData that we've covered so far, those are primitive types. There are also dynamic or reference types, which we'll be talking about shortly. When we declare variables like we have done already, that is by saying things like let myCount equals 100, we are creating a value type. For those of you who know what a programming stack is, value types are stored on the stack. For everyone else, you can think of value types as storing the data as part of the variable. In a primitive type, the variable and the data are essentially the same. You can be guaranteed that every time you create a value type variable, its value will be directly tied to the variable and no other one. Value types are the lowest level implementation of data in JavaScript. Let's go back to programming in our app.js, which is read by our HTML file, rather than just typing into the console prompt. This is what we'll be doing for the rest of the course. When you first set a value type to some data, whether that is initializing it directly when you declare it by saying something like let myCount equals 101, or by doing it in two lines, first let myCount, then myCount equals 101, you are essentially telling JavaScript the type of the variable. 101 is a number, so the type will be a number. If you had said myCount equals quote 101 quote, then you are creating myCount as a string type, that is. There are several primitive types in JavaScript: string, number, big int, boolean, symbol, null, and undefined. We've already shown examples of string and number. Big int is meant for very large numbers, boolean is for true or false, and symbol, something you will not likely use often, is for creating a unique value, typically used as a property value, which we'll talk about soon. Null and undefined are unfortunate constructs created by the JavaScript designers, which in my opinion was a very bad idea. But unfortunately, we have to live with them. I can promise you that if you program JavaScript for more than 5 minutes, you will have problems created by these. An example of undefined is this. If you just declare a variable without setting anything to it, it automatically gets the type undefined. Null is sort of like that, but I think of it more as undefined with a purpose. You explicitly have to say something like let myCount equals null to get the value of your data set to null. In many other languages, you explicitly declare the type by saying something like int myCount, then forevermore myCount is an int. In JavaScript, everything is implied. Don't be confused though, just because it's implied doesn't mean it changes throughout your program. It does not. Once you have created a variable type, it remembers that until you redefine it, if you so choose. To find out exactly what type a variable is, you can use the function typeOf. Because we assign myCount to quote 101 quote, it's going to be a type string. Let's verify that. We can enter console.log, then the typeOf function, and in parens, myCount. In order to see the output, we do need to bring up the console again. After doing that, we see the output is indeed string. If we change myCount to just 101, the type is number. And if we change myCount to true, the type is boolean. That shows that the value we set our variable to creates the type of that variable. Besides primitive or value variables, we also have dynamic or reference type variables. The difference is that reference type variables point at some data that is represented by the variable, as opposed to value type variables actually hold the value. For those of you that know what stacks and heaps are, primitive type variables store their data on the stack, and reference type variables store their data on the heap. If you don't know what that means, that's okay. You can think of reference type variables as just simply pointers or references to some real data, or even a function, which I know we've not talked about yet. What are the things that we point at with reference types? I could say anything of type object, but that would be a really annoying answer. Typically, reference types are objects, functions, collections, arrays, or dates. Let's talk about objects right now. Objects typically are things that contain multiple attributes or values associated with them. You could think of maybe a house as an object. Then the attributes of the house might be address, color, number of rooms, owner, or pretty much anything that you want to associate with a given house. When you declare an object, you are essentially declaring just one instance of that object. So, for example, I might declare a variable named myHouse and assign it all the right attributes. For our case, and the example we will use, is we want to create a planet reference variable and assign the attributes name, associated star, diameter, and gravity. Let's head back to our Visual Studio Code in our app.js file and create an object in JavaScript. With what we currently know about how to use primitive variable types, we could create variables for each of these. That is, we would say const planet name equals Earth, const planet associated star equals Sun, const planet diameter equals 8,000. Of course, we know that's miles. Const planet gravity equals 32.2, which we of course know is feet per second squared. Those are all value types. Let's up our game and turn them into reference types and just name it planet Earth. That would be const planet Earth equals open curly brace, close curly brace. That is typically referred to as a JavaScript object literal. And then the way JavaScript objects work is that you create key value pairs inside the object literal curly braces with the key and value separated by a colon for each attribute. In our case, we have 4 key value pairs. Let's create those and drop off the redundant name planet from each. That's just name Earth, associated star Sun, diameter 8,000, and gravity 32.2. If the syntax looks a little funny, no worries. My experience in learning new languages is that syntax always looks funny until I get used to it, then it looks totally normal. The way object syntax works is that you create a list of properties in the format property name, property value, followed by a comma. After the last property is defined, the comma is optional. You might think that having an optional comma like that is weird, but it turns out it's very useful. If you want to add another property, it's easy and you don't have to remember to go back up a line and add a comma, something I often forget to do. The last thing to do, and the most satisfying, is let's console log planet Earth and see what it looks like. We just say console.log and then pass planet Earth as the parameter. The debugger pretty much just shows us what we put in, but if we click on the little caret, it expands and shows us the properties exactly as JavaScript sees them. Now that you've created a reference variable type, how do we access the key value pairs by property name inside the curly braces or the JavaScript literal? That's easy. There are 2 ways to do it. The first and most intuitive is by using dot or period notation to reference the data. To get the name, we just do console.log planet Earth.name. Of course, it's called dot notation because we're using the period to reference properties in a reference type object. Refreshing our browser on the right, looking at our console output, sure enough, we get the value Earth. We could do the same for the other three attributes, but I'm sure you get the idea. The other way is called bracket notation, and the way that works is that instead of the dot, we add a left and right square bracket after the reference type variable name, and in between the brackets, we put a string value with the name of the property we want to get. Say, for example, we wanted planet gravity, we would just say console.log, planet Earth, open bracket, quote, gravity, close quote, close bracket, and then an optional semicolon, which we'll talk about later, but just for now, remember that semicolons are always recommended, but also optional, which is cause for a complete course all on its own. Refreshing the browser, we get 32.2 as expected to the console window. Notice I said we put a string value with the property name in between the brackets. I chose my words carefully because I could have just as easily said we put a JavaScript primitive variable of type string in between the brackets, and I would have been just as correct. Let's do that. Above our planet Earth reference variable, let's create a primitive variable, const property to get equals gravity in quotes. Then replace our quoted string, gravity, with our variable, property to get. Refresh our browser, and out comes the same thing, 32.2. That's the reason we have the bracket notation way of accessing properties of an object. We may want to programmatically set the name of a property and then get that rather than knowing ahead of time the name using dot notation. As you'll see going forward in the course, and actually the rest of your life programming JavaScript, bracket notation is wonderful to have. The downside, though, is it's easy to misspell the names of properties, unlike dot notation, which you likely get an error before the program even runs. If you do misspell, the bad news is you get returned the completely valid type undefined. That's really bad, because those kind of errors can surface later when your app is running and be difficult to track down. The other question you might be thinking about is how do you update reference type variables? You can almost guess, which to me means the designers of JavaScript did a great job. To update gravity using dot notation, you'd just say planet Earth.gravity equals 32.17, assuming you wanted to update it to be more precise. And using bracket notation, that would just be planet Earth, open bracket, gravity in quotes, close bracket, equals 32.17. These two do exactly the same thing in updating the gravity property of the object. JavaScript, like almost all other languages, has arrays. Arrays are just a list-like object that you can assign to a name. The list of things you can include in an array can be value or reference types. Typically, arrays are lists of all the same type things, but you can just as easily mix and match types. Unlike the JavaScript objects we learned in the last clip, where we reference properties with either dot notation or bracket notation, finding an individual item in an array can only be done by using a zero-based integer offset into that array. That offset is often referred to as just an array index. An example of an array could be this. This array has 4 items in it, also referred to as having a length of 4, with the first 2 items being numbers, the third is a string, and the fourth is a boolean. Though I'm not showing it, arrays can also contain references to other objects, even including other arrays. It's perfectly reasonable in JavaScript to have arrays of arrays of arrays, though that may get a little confusing. Let me show you what I mean by example. Specifically, let's create an array of planets of our solar system. For now, though, let's just start out with the first 3. We declare the array just like declaring a value or reference variable. That's just const planets equals. Then we start out with just a left and right bracket. That's also referred to as an array literal. Remember, open and close curly braces was referred to previously as an object literal when we were working with objects. Then we create a comma-separated list of values. Our first three are Mercury, Venus, and Earth. Notice that I use const instead of let. I do plan on updating this array, so how does that possibly make sense? Well, object types, of which arrays are, unlike value types, store a reference or location of the array and not the actual data in the array. When we update the data in the array, we are not changing the reference to that data, so const is recommended and not let for working with arrays. There are cases where you might want to change the reference to an array, and then let would make sense. But for our case, and in most cases you'll probably run into, const is correct. To see what we've created, we can just do console.log planets. Then, saving the file, the browser automatically re-renders, and we can look at the console for our output. You can see the items of the array listed next to their index. This is exactly what we would have expected. The easiest way to reference items in an array is by using the offset or index into the array to get the value. Say we wanted the second item in the planets array. Since the first items would be planet square bracket 0 square bracket, the second item is just planets square bracket 1 square bracket. Let's output that. Console.log planets sub 1. Saving the file, the console shows Venus as expected. To update a value in an array, we just put the array reference on the left side of the equals. That is, if we wanted to replace Venus in all lowercase to Venus in all uppercase, we just say planet sub 1 equals, double quote, Venus in uppercase, close quote. Saving the file, notice that just the second item has changed as expected. Arrays also are dynamic, which means we can change the length of an array by simply assigning a value to the new index. It does not even have to be in order. We could say planet sub 5 equals Saturn. Then save the file, and the array length is now 6, with 2 empty values between Earth and Saturn. I mentioned earlier that an array is an object. That means that we can use dot notation on our array. As an example, we could console.log planets.length, and now we'd get back 6 as the length of the array. There's a lot of other built-in functionality to objects that we can use in arrays, and we'll get to that later in the course. JavaScript functions are pretty much the same as functions in most other languages. Sometimes they are referred to as subprograms or subroutines, but basically they all do the same thing. You can think of a function as a grouping of code with a common purpose. Sometimes that purpose is to do something independent of where it's being called from, and sometimes it's meant to return something that it figured out or calculated. Let's make an example of a function that does something useful. How about a function that writes to the console our current date and time? In our program, that is our app.js, one way to create a function is as follows. First, the word function, then the name of the function, that's how we'll call it, followed by open and close paren. Then the body of the function, enclosed in curly braces. In this case, all we want to do is output the current date and time. The code we will write inside the curly braces is identical to the code that we're writing before without any functions. That is, our console.log above will work inside the curly braces exactly the same as outside. So let's make a console.log that outputs the current date and time. That's just this, console.log new date. That essentially just outputs the date to console.log. All that's left is to call our function. The way we call it is we type its name, then attach to the end of the name an open and close paren. That open and close paren essentially executes the function. Let's see. Save the file. Sure enough, on our console, we get today's date and time. Another feature of functions is that we can pass JavaScript variables to them. That is, anything we declare with let or const, like above, we can pass into the function by putting it between the defined open and close parens in the function definition. Let's say, for example, we wanted to pass a person's first name into the function so that function could log a friendly message with the person's name in it. Let's add what we call a parameter to the function so that the function can have access to it. We do that by putting between the parens the parameter name in our case. Then in the function, instead of just outputting the current date, pre-append to that date a message. We can do that by adding some output to the console log that says, quote, hello, quote, plus the variable name, plus, quote, the date and time is, plus what we had before, new date. We've not talked about it yet, but the plus operator simply pushes all the things around it together. Now, to get a name into that function when it's called, add a variable to the calling of that function. That is, add it between the parens of the call show date time. One way to do this is to first create a variable. Const name equals John. Then add name to the call. That's it. Saving the file, looking at the console output, there you go. Hello John, the date and time is, followed by the current date and time. That was an example of having a function do something for us, that is, outputting the current date and time with a friendly string attached to it. But it also turns out functions can return information to the caller. Let's say we wanted to create a function that we could call, that we could pass in a diameter, like a planet diameter, and it would return to us a radius, which would just be half the planet's diameter. Let's do that. Create a new function, call it getRadiusFromDiameter. Remember, I like descriptive names. Have it take a single parameter, diameter. Then we can calculate a new variable called radius. Just doing some simple math, that's const radius equals diameter slash 2. The slash is the JavaScript divide symbol. Then, to get the value out of the function and back to the caller, we use the return statement. Return radius. Now, call the function. GetRadiusFromDiameter, passing in planet Earth.diameter from before. Because we returned from inside our function the answer, or the radius, we can capture that by having the function assign to a new variable the result. That's simply by adding const radius equals in front of our function call. After that, output radius, that's just console.log radius, and that's it. Saving our page, looking at the console, there's our output, 4,000, half of 8,000, just what we expected. I left out a lot of details here that are very important. Things like, is the radius variable inside the function the same as the return variable? Well, the value is, but the variable is not the same. We'll talk about that and a lot of other important things regarding functions later in the course. Functions are really what makes JavaScript powerful and are my favorite part. Let's talk a little bit about Lambda functions, which were first introduced in ECMAScript 6, which is a definition specification for JavaScript. Lambda functions basically are a shorthand way of writing the same thing as we did here when we declared function getRadiusFromDiameter with a single parameter and returning radius. If I wanted to write that exactly the same way, but as a Lambda function, I could comment this code out, and then I would say const getRadiusFromDiameter equals, and then the Lambda syntax is you first define the parameter coming in, diameter, and then you put the fat arrow, which is equals greater than, and then what you want returned from the function, which is just const radius equals diameter divided by 2, and then return radius. Saving this file, the right-hand console just updates with the same 4,000, so that works exactly the same way. Well, what about if we were to move the function below where we call it? So let me comment out the Lambda function, uncomment the function definition from before, cut it, then paste it below where we use it, and save that. Well, it still works. What about the Lambda function? Well, let's see if that works also. Let's comment out our function definition, uncomment our Lambda function definition, cut that, paste it, and put it below our console.log like we did for our function when it worked. Save that, and we get an error. The reason is that functions are automatically hoisted to the top of any function where they're used. That is, you can declare a function anywhere, and it will be as if you declared it at the top of the function, and you can use it anywhere. Lambda expressions, not so much. As the error says, you cannot access getRadius from diameter before it's initialized. So that's one big benefit of using functions versus Lambda functions. So are there other benefits to Lambda functions? Well, one big benefit is the syntax can be a lot more convenient if you take advantage of some of the shortcuts. So for example, if this were just a single line return, in other words, instead of doing this function in 2 lines of code, we get rid of the return radius. We simply return diameter over 2. We could make that same simplification in our function, but it wouldn't be that much simpler. However, with Lambda expressions, if it is a single line return like this, you can do it all on one line by removing the return statement itself and the opening and closing braces, and we get exactly the same result. In addition, if it's just a single parameter being passed in, we can get rid of the paren on the left and the paren on the right, and this expression is exactly the same as what we had before. This basically means getRadius from diameter is a function that takes one parameter and returns that parameter divided by 2. Do I use this often in the course? Well, it turns out I really don't. Functions are more convenient for me because I can define them and use them anywhere, and I don't need to be concerned about the order. There are times when I do use Lambda functions, though I'm not sure I do in this course. Typically, if I'm doing something like a filter where I'm passing in a function, it's much easier to use Lambda expressions than it is to pass in a function just because of this nice, simple syntax. Our plan going forward for the rest of this course is to learn practical, modern JavaScript programming by doing. That is, the first 2 parts of this course were about the absolute basics and the things that are fundamental and easiest to explain following a definition-like format. I get how boring that can be, but now that we are through that, we can launch into the much more fun and engaging part of the course. The plan is to cover enough JavaScript so that you can build interesting and compelling apps. There is a lot more to JavaScript than we are covering in this course, but I'm confident that once you've completed this course, you'll easily be able to incrementally add knowledge on your own about JavaScript. I want to keep this course focused on JavaScript, but to build a fun app, we need a little bit of HTML and graphics. We'll use the HTML canvas element as the basis for that, as well as some Canvas API calls. Almost all of our work will be with JavaScript programming, and what little we do with Canvas will not be much of a distraction. By the end of this course, we'll have an app built that looks like this: 8 planets orbiting the sun, 2 of those planets having moons orbiting them. By the end of this module, we'll have just the Earth sitting in a stationary position, waiting to be animated in the coming modules. In the process, we'll learn about the canvas element, and we'll also build some functions that do things like draw the sun, draw the Earth, and their orbits. We'll generalize those and at the same time learn about an interesting new way to pass parameters in and out of our functions using what's called object destructuring. Let's do it. The plan for building the graphics part of our app is to use the Canvas API, which is built into HTML5. The Mozilla docs are a great place to start to look at how to use those docs and explain what they actually are. The Canvas API gives us a mechanism for drawing using JavaScript to the HTML page. As it says here, it can be used for things like animation, graphics, and data visualization. We're going to use it to draw our solar system and move the planets and some of the moons around our sun. To use the Canvas API, as it shows here, we need to put an HTML element on our page named Canvas, and we need to associate it with an ID so we can reference it from JavaScript. Then, when we look at the JavaScript section underneath the Canvas API, we have a really simple example of how we can use it. The first line, const canvas equals document.getElementById, Canvas, that actually gets us a reference to that element on our HTML page. Then const ctx canvas.getContext2d, that uses a reference to the document ID we just got and then assigns a context we can use to write information to that element, like, for example, circles and squares. You can see from the example here, ctx.fillStyle equals green says that any write commands we do to that context, we want them to be filled with green, and then the next thing we do is we write to it ctx.fillRect, which is fill rectangle, and we give it the coordinates of our rectangle box, 10, 10, 150, 10, and that should give us a green square just like this. Let's do the same thing in the demo code that we set up in the previous module. As a reminder, here we have our index.html, which simply includes our source/app.js file, that's our JavaScript, and then renders a body to the page. Since Canvas uses modules internally, we need to add type equals module to our script include page. For our body, let's just replace our h1 tag with the canvas we saw in the docs. That's just this closed canvas element definition. Let's expand it by assigning it an ID and call that ID solar canvas. For our purposes, let's give that a width of 380 and a height of 300. That's essentially the box that our canvas is going to be able to write to, and it also is the units that we're going to use when writing to it. To help us keep track of where the box is on our screen, let's create a border by saying style equals border and give it 1 pixel as the border, and let's make it a solid gray kind of color. Navigating to our JavaScript source, looking at that app.js, we had a whole bunch of example code. So for now, let's just select all that code and start from an empty file. Let's follow the pattern from the Canvas docs. That's just const canvas equals document dot get element by ID, and we'll pass it the ID of our canvas. Then let's create the context. That's just const context instead of ctx like in the docs, and then we'll just say canvas dot get context. Tell it we want a 2D context, which is what HTML Canvas is best at. And then we're going to give it the option alpha false. If we want the green rectangle, like in the example, we would just say context.fillStyle equals green. Then we fill it, passing the parameters 10, 10, 150, 100. That's basically all there is to writing graphics to an HTML Canvas element. Now, when we click on our live server, remember that's a plugin from Visual Studio Code, press go live, and we get our browser now with the green square inside our Canvas element. Now that we've proven that we can write to our graphics API context, that's our canvas, and put a rectangle up, let's start with our real solar system app, and let's put a sun right in the center of our panel as a yellow circle. Remembering that our coordinate system basically is a width of 380 and a height of 300, Essentially that's 0 to 380 and 0 to 300. Let's create the sun position in the center. Let's just say const sun position. That's going to be for defining a JavaScript object. And let's call the x 190. That's about the center. In the y 150. Again, that's about the center. Now, let's make another object that's the actual sun data. So const sun data equals, and now we're just making up key value entries. So let's give the sun a name, and we'll just call that sun. Give it a color, yellow. We talked about that already. Give it a radius of 9, and then assign it a position on the screen. That'll just be sun position dot x, and make the y just sun position dot y. Rather than making our calls directly to our Canvas API, let's create some functions that we can call to do the work for us. Let's make two functions, the first one named clear and the second drawStar, and then we'll write those functions following that. First, call clear as a function named call, and then we're going to pass it context. It turns out that we don't actually have to pass context if we're going to create the function right here, which I am, because context is declared already. So to create the function, I'm going to say function clear, and then the first parameter is context. All I'm going to do is call context.clear, rect, for rectangle, pass it the coordinates that I want to clear, which is just 0, 0, to canvas.width and canvas.height. And that's essentially it. I don't have to return from a function. The function will automatically return. Now let's draw the sun. The function we'll create is we'll say drawStar, so it could draw any star even though it's our sun. And then we're going to pass as the parameters, again, context and our sun that we just defined. Let's scroll up to give ourselves some room. Declare the function, function drawStar. First parameter is context, and the second parameter is sun data. Just a side mention, everything we're doing right now is stuff that we learned in the basics section. Momentarily, we'll get to expanding some of what we did earlier with really useful things. So for now, this is just a repeat, but doing something useful with what we learned earlier. For drawing our star, let's just say context.beginPath, because we're going to draw an arc for our star. So this basically just starts the arc. Then we're going to give it a color, context.fillStyle equals, and here we could say sundata.color, just using dot notation to set the color. But my preference is to destructure all these values before we use them so they're local to this method. So that would be const color equals sundata.color, and then the reference here would just be color. We could do the same for name. That's just const name equals sundata.name, and on through the other three parameters. There's a shortcut we can take to avoid all this destructuring of data. We can replace the parameter in our function with an object literal, which is just open and close curly brace, and then reference directly the properties of that object. So this just becomes color, name, radius, x, and y. Now I don't need to do these extra dereferencing steps, and I can continue writing my drawStar function. Context.arc. First the starting positions, x, y, then the radius of the circle that we want to draw, then the starting angle, 0 in our case, And then we're going to give it the circumference, which is just 3.14159265 star 2. And the final parameter is whether to draw the arc clockwise or counterclockwise. Then we want to fill the arc. That's just context.fill. And then we want to close the path. That's just context.closePath. That should be all we have to do to draw a yellow circle, which is our sun, in the middle of our canvas. Pressing the Go Live button, that refreshes our browser, and sure enough, there's our yellow sun. You may have noticed in the last clip that I used pi as 3.14159265, and I also multiplied it by 2 to get the circumference. Well, there were two things that I pretty much snuck in there. One is I could have mentioned pi using a math library that's in JavaScript, and I also said star 2, meaning multiply by 2. And of course, this is a beginner JavaScript class, and that shouldn't be obvious that star means multiply. So let's talk about the math operators in JavaScript that you commonly use. Before doing that though, let's create a little test page that we'll use for the rest of the course to demonstrate things that really don't want to involve the full app. So let's create a new test.html in our root folder, and let's copy the code from our index.html, put it in test.html, and instead of app.js, let's just import test.js as our script. And then, of course, add it to the scripts folder, test.js. Now, if we switch back to app.js and we grab what we did with pi times 2, then switch back to test.js and we say console.log, and then we put that in there. We actually just pasted a JavaScript expression. That's basically what you get when you put in anything that involves arithmetic operations in JavaScript that creates an expression. So now, if we go back to our live server, browse to test.html, bring up our debugger and the console window, and we get our final result, which is 6.2831853. So what are the other arithmetic operations? The basic 4 are just add, subtract, multiply, and divide. The other 2 are remainder and exponentiation. And there are also other bitwise operations that you'll not use very often, likely, and you can certainly read about them if you need to. The other thing I didn't bring up was how to specify pi in a better way than explicitly referencing the digits. Turns out built into JavaScript is a math object which has lots of different properties and methods associated with it. Browsing to that, you can see on the left panel all the different properties and method, including math.pi, which is what we'll use instead of explicitly referencing the numbers. You can see there's all these different methods, math.cosine, math.sine, which we'll actually use later for our planetary calculations. But as I said, the library is quite extensive and very useful. Let's now also go back to our app.js and replace our constant, which represents pi, with math.pi. And while we're here, let's remove the initial code we wrote to put the big green block up on the display, since we've replaced it with our nice yellow sun. Our plan is to draw more than just the sun in our solar system, so we need to generalize our draw star sum. In the process, we'll learn a little bit more about destructuring objects and show some useful techniques along the way. We're back in our app.js, and the code that we want to pull out, or refactor, is from drawStar into a new function, drawSpaceObject. So let's start out, scroll up a little bit just to give us some more space, and let's create drawSpaceObject. Function drawSpaceObject. And previously we passed our color, name, radius, x, and y as properties of an object, but this time let's pass them as straight parameters. Sometimes it's more convenient to have straight parameters, and sometimes it's easier to pass an object with properties, so I'll demonstrate both. In this case, there's not that many, so let's just do it as parameters. That's first context, then color, then name, then radius, then x and y. Since drawStar basically is the same at this point, let's just pull the code from drawStar, put it into drawSpaceObject, and then from drawStar call it. That's just drawSpaceObject, context, color, name, radius, x, and y. Saving the file, the browser renders with no errors. You may have noticed when we declared function drawSpaceObject, the name parameter showed up a little less dark than the other parameters, meaning that Visual Studio Code doesn't think that we used it. Well, that's because we didn't. Let's take care of that by putting a label above our yellow star with the name of the planet, sun in this case. In our drawSpaceObject, let's first define a font. That's just context.font equals, and make it 9 pixels high. Let's set the fill style to white. Let's align the text in the middle. That's just center. And then let's actually write the name. Fill text. And the parameters are just name, x. Let's back it up a little bit from the center, so we'll just say y minus radius minus 5, just to add a little buffer there, and save that. Notice now on top of our nice yellow sun, we have the word sun. That's about all we're going to do for the star, so let's now add a planet, and we might as well add planet Earth. Scrolling back up to the top of our file, let's just add it below the sun. So that's just going to be const Earth data equals, and we'll make this an object just like the sun, and let's name it Earth, because of course we're going to want a label on it. Let's give a color. Blue's a good color for the ocean. Give it a radius. I'm going to call it 5.1. Don't go too crazy trying to figure out what these numbers mean. They're just numbers to try to make the picture look good. They're not actually accurate or scaled. Let's call the distance 110. Remember, our canvas is about 300 wide. Let's say we want to start it at 90 degrees. So let's give a starting angle. This is a new property. And incidentally, you can just declare new properties. There's nothing you have to do to type Earth data or any other object for that matter. You can just declare things. So I'm saying angle colon, and 90 degrees in radians is just math.pi divided by 2. Very convenient. And then, because at some point we're going to want to set this thing in motion, let's make the angle change rate 0.013. And I only know that because I've reversed engineered it after I got all this working, and that looked pretty good. So let's now add Earth below our sun. So scrolling back down to the bottom, after we drew our star, let's now draw Earth. We need to know where to put it, that is the x and y, and we're going to want to put it to the right of the sun. So let's define two more variables, planet x and planet y, for where we want this Earth to go. Defining them as local variables, const planet x equals sun position dot x plus Earth data dot dist star 1. The idea is we want to put it one distance increment from the sun position. You can think of the dist as the radius of the orbit. Then for y, const planet y equals sun position dot y plus the same thing, Earth data dot dist, but this time, since we want to put it at the same y or level as the sun, we'll multiply that by 0. Later, when we start moving planets around, we'll add some sines and cosines to make planet X and planet Y more interesting. So now, let's draw the planet. Let's just draw space object. First parameter is context. Then Earth data dot color, Earth data dot name, Earth data dot radius, and then lastly, planet X and planet Y. Saving the file, Earth pops up on our canvas in blue, just as we expected. To help you understand, if we change this to -1, notice the Earth just goes on the other side of the sun, but we're going to leave it 1 for now. We've successfully added our sun and our first planet, Earth, to our solar system. Let's now add an Earth orbit line to our canvas. Scrolling down to where we actually drew Earth itself, let's add another line calling a function we've not yet written called drawOrbit. Let's pass that our context like we always do, our sun position dot x, our sun position dot y, and we want to trace the Earth's orbit. So that would be Earth data dot dist. Now let's simply implement drawOrbit. The declaration is going to be function drawOrbit. The incoming parameters are going to be context x, y, dist. And for the function itself, similar to what we've done before, context.beginPath. Then draw the arc, which will be our full circle, just context.arc, x, y, distance, which is the radius of the circle, 0 for the starting position, and then math.pi times 2 for the circumference, and then true to have it draw clockwise, which really doesn't matter. Then set the line width. That's just context.lineWidth equals 0.5. Set the stroke style. That's just context.stroke style equals white. And then execute the stroke itself. Finally, close the path. That is the path that we just defined as our orbit. Saving the file, you can see now we have our Earth orbit as a full circle. The final thing to talk about in this module is separating out different functions into different files in our JavaScript project. The reason we do this is it allows our variables to be isolated from each other and not accidentally clobber one another by redefining the same name twice. It makes it really clear what the interface to our functions is. It's easy to share these new functions among different projects, and it's easy to test to make sure they really work. Let's move back to our solar system project and separate out several of the functions we defined in there and put them each in their own modules or files. The way ES6 modules in JavaScript works is that you typically take a function or a constant, in this case we'll take functions, and you move them to their own separate file. Then you import the reference to that function back into your main file and call it. Let me explain what I mean. If we look at our function drawSpaceObject, what we can do is we can take all this code, put it into a copy buffer, add it to a new file in its own folder, which we'll call lib, and let's call that drawSpaceObject.js. Paste the file in, and there's only one thing we have to do in addition. We have to say export, and then we put in squiggly brackets, which basically says make it a named export, and export drawSpaceObject which is the name of our function. A shortcut way to do the same thing is we can simply add the word export up above. Now, when we go back to our main app project, let's remove this function, and then at the top, import a reference to it. And we do that by saying import, and then we put in squiggly brackets, draw space object, and we now say from ./lib/ draw space object .js. Now, when we save this file, our app works exactly as it did before, but we no longer have draw space object in our app.js file. Let's do the same thing for draw star and drawOrbit. First, draw star. This time we'll just cut it directly. Draw star.js. And then we'll type export, paste in the result. That's our function. Go back to app.js. Do the same thing for drawOrbit. Cut it out, add it to our lib folder, type the word export, paste in the function, and then back to our app.js, we import both of those. One last thing is if we look at draw star, we notice that we use draw space object in that, so we have to do the same import in draw star as we did in app.js. Notice that we did not import it from the /lib folder. That's because draw star and draw space object are in the same folder. Now we've got three separate files, drawOrbit, draw space object, and draw star, each in their own individual files, and they're all referenced from app.js. This is a much cleaner way to implement JavaScript code. At the start of the course, we did talk about arrays for a few minutes, but we're going to dive in a little bit deeper now, as well as provide a real-world example using our solar system to demonstrate working with arrays. Specifically, we're going to go through more details on creating arrays, adding items to the beginning and the end, accessing and modifying them, finding items in an array, maybe by name, removing items from an array, and iterating over them with for loops. By way of review from our previous module, an array is just basically an object that you can assign a list of things to. Those things can include value types or reference types, and the array itself is a reference type, which means it has properties like length associated with it. Also, the array can contain multiple different types. So as you can see here, the first two items of this array are value types, just numbers. The second is a string, and the last one is a Boolean. We're back here now in Visual Studio Code, and let's go through all the examples of the different operations we just talked about that we can do with arrays. The way we're going to demonstrate those is similar to how we did operations in an earlier clip. We have a test.html file that includes source/test.js as a module. Test.js is just the JavaScript. The console log is running on the right side of the screen, and the way we executed that was we ran a browser in another window with test.html. Now basically everything we do will be rendered to the console on the right. So let's comment all this code out. You see the console log completely disappears. And now let's create a simple array of planets. That's just const planets equals Mercury, Venus, and Earth. Let's console log our planets array so we can see it in our log. And then above that, let's do our operations. The way to add to an array is to use the push method on the planets array itself. So that's just planets.push, and then we pass in the name of the new planet we want to push to the array. And you can see in the log now we have 4 items, and the last one is Mars. Modifying arrays is easy. All we have to do is reference the item in the array we want by a zero-based modifier. So for example, if we wanted to modify Venus, Mercury is the 0 item, Venus is the first item, Earth is the second, Mars is the third. So we would just simply say planets sub1 equals, and if we wanted to make it Venus in lowercase, we would just say Venus. And now you can see in our log, Venus is indeed lowercase. To find items in an array, the easiest thing to use is the index of function on an array. So in this case, if we wanted to output the index of the array item Earth, we would just say console.log. Then we say the array name, which is planets, index of, in camel case, the function happens to be camel case, and then we would just say Earth in the proper case. Saving the file, you can see the result is 2, because remember, Mercury is item 0, Venus is item 1, and Earth is item 2. Removing items from an array is a little more tricky. There's actually 3 different ways we can easily remove items from an array. Say we wanted to remove just the last item from the array. We could just simply say planets.pop. Saving that, notice Mars disappeared, and now we just have Mercury, Venus, and Earth again. If we want to remove an item from someplace that's not the end, we can just say planets, then use the splice method. The first parameter is the position, the index to splice. So say we wanted to splice Venus, we would say 1, and the second one is the number of items to remove. I'll say 1 again. Saving that, notice Venus disappears. The final method we can use to remove an item from the array is to use the shift method. Shift just simply removes the first item of the array, or actually the 0th item if you're counting the index. That would just be planets, shift, saving that, and now all we have left is Earth. Those are the 3 ways you can remove items from an array. The final thing to talk about is iterating over arrays. Say, for example, we wanted to iterate over the arrays after we added Mars. We could simply type for, then const, planet of is the keyword that gives us that iteration, planets, and then when we say console.log, planet, save the file, here we have all 4 of our planets in order. Mercury, Venus, Earth, and Mars. Now that we've got a little bit more information about arrays, let's modify our app that we've been building for our solar system to use arrays to create 3 planets in our solar system. Eventually, we'll create all 8, but for now, 3 is good enough to get started. So we're here in our app.js. Notice we have our Earth data defined, and then we call drawSpaceObject with Earth data. Let's, instead of having just Earth data, let's create an array of planets. That would just be const planets equals, and we'll create an empty array for now. Following best practices, let's extract all our planets into a separate file. So in our live folder, let's create a new file called planetdata.js. From our original file, app.js, let's cut Earth data from there, go back to planet data, create an export of planet data, just like we did previously, but this time we're exporting data as opposed to a function, and that gives us Earth. Let's now do Mercury and Venus the same way. Going back to our app.js file, scrolling up to the top, we can now import those instead of declaring them directly. Just import, and it's a named export, so I can put it in curly braces. Mercury data, Venus data, and Earth data from /lib/planet data.js. So far, we haven't actually done anything. Let's add to our planets array our 3 planets, Mercury data, Venus data, and Earth data. So that's it for now. We've basically created ourselves an array of 3 planets that we'll use coming up to rotate those around our existing sun. Let's take a look at what we've got now. We've got our planets array defined with our 3 planets that we want. At the moment, all we're using is Earth data, and we're rendering that right below our draw star. So how about if we add to draw star something that also draws the planets? To do that, rather than pass a new parameter into draw star, let's add to our sun data a new property, planets, and let's reference the planets array we just defined. Notice it's defined after we declared our sun data, so let's take that planets array and move it above our sun data call, and now it'll work correctly. One shortcut we can also take is that in ECMAScript 6, if you have the same property named with the same variable, you can simply replace planets with just a single planets, and you get the same thing. That's a very convenient shortcut that you'll see a lot. So now we want to move our Earth data drawSpace object into our draw star. So let's pick up this code right here, which includes both the drawSpace object and the drawOrbit. Cut that from here. In draw star, since we added a new property to the second parameter, that is this destructured object, which we passed in as sun data, let's add another destructured property, planets. Then we can paste in the code that we copied a moment ago, and that gives us the ability to draw one planet. But the reality is we want to draw all the planets, so let's use our iteration syntax of arrays. So let's say for const planet of planets. And let's put this whole block of code into that iteration. And now replace Earth data with planet. Notice also that we don't have sunPosition.x and sunPosition.y anymore, but we do have these variables passed in x and y. One thing we can do in JavaScript with incoming properties like this is we can again use destructuring, and we can rename that to x star and rename y to y star. What this does for us now is we can reference these as x star and y star instead of just x and y, which might be a little confusing. So when we draw our star, or our space object, which is the sun, we now draw x star and y star. And here in our planet position, we change that sunPosition.x to x star and sunPosition.y to y star. And the same thing for drawOrbit, x star and y star. One more thing we need to do is, since we're using drawOrbit now inside of our draw star, we have to import that. Let's just import drawOrbit from, and we're in the same folder, lib. We can just say /drawOrbit.js. One last thing to do before we browse to our app and see how it works is let's go back to app.js, and then now the two imports that we have at the top, drawSpaceObject and drawOrbit, are no longer necessary, so we can remove those from our project. Now, saving the file, we have Mercury, Venus, and Earth all lined up as we would have expected, orbiting around the sun. Another very powerful feature that comes along with JavaScript ECMAScript 6 is the spread operator. What the spread operator does is it allows us to enumerate all the values of an array just by saying ... So for example, if I wanted to create a new array out of planets, I would say const planets data equals, and then I could simply say open square bracket, close square bracket, and then say ... planets, and that would essentially copy all the planets from the original array planets into a new one, planets data. And incidentally, planets data is a new reference, so if we were to check and see if planets equals planets data, we would actually get false because they're pointing now at different places. So what can we do with this? Let's say we wanted to add another planet. All we'd have to do is in our array brackets, add a new object, and this time I'll just type it in directly, Mars, with the following attributes. Notice I put it in the array first, so when we look at the array, it's actually the first entry there. Then to our sun data, we simply now assign planets to planet data, because we no longer can use the nice shortcut of planets being equal to planets. Saving the file, and we now show Mars as our fourth planet, as expected. To demonstrate the spread operator in a little more detail, let's console log out the new planets data array. That's just console.log planets data. Bringing up our console window, refreshing our browser, you can see our 4 planets. Notice Mars is the first one in the array because that's how we added it with the spread operator. We could just as easily make Mars the last entry in the array by grabbing the object and putting it at the end of the array. Now notice in the console window the current order was Mars, Mercury, Venus, Earth. Saving this, the new order is Mercury, Venus, Earth, Mars, because it's at the end of the array. You can imagine that we could do all kinds of things by splitting the array and adding multiple array items around the planet's array, and the array would just modify accordingly. The spread operator is a very powerful way to work with arrays to manipulate the values inside them. This module is going to focus on iterating and looping in JavaScript. We'll start out by talking about the basic for loop that's basically been available in JavaScript from the very beginning. It can handle every case, but it's a little awkward to work with in many cases. Then we'll move to the for of loop that iterates over iterable objects, including built-in strings, arrays, or array-like objects. It also invokes a custom iterator if you have that. For in iterates over all the enumerable properties of an object that are keyed by strings, including inherited enumerable properties. We'll then move on to the while loop and the do while loop. Both of those are very similar, and they basically check a condition to see whether to continue or not. Following that, we'll move on to forEach and map. ForEach is specifically designed for arrays and is very functional, which you'll see what I mean coming up. And the same thing with map, which is actually my favorite way to iterate over a collection and pretty much my go-to function that I use almost all the time. It's rare that I use a for loop in my actual programming. Finally, in this module, we'll update our solar system application to include all 8 planets from just the 3 that we've got right now. We currently are using the for of loop. We'll convert that over to my favorite map function, and then later we'll see why mapping is just incredibly useful when building JavaScript apps. We're here back in Visual Studio Code, and instead of looking at our solar system app, we're looking at our test.js, which is included from our test.html, meaning that we've browsed to test.html in our browser. Below in the console is our output. So let's clean this up a little bit and get rid of everything below const planets. Let's start out looking at a for loop. A for loop syntax is basically you type for, And then in parentheses, you put three things separated by semicolons. The first is the initialization. The second is a condition to check, and that's to see when to stop iterating through the loop. And the third is a final expression to be run after each iteration. We could write the statement directly. My preference is to always put in curly braces what you want executed on each iteration of the for loop. So for our planets, this would just be let I, and I'm going to use I as a counter, equals 0. Then the second thing is the condition. So we're going to say I is less than planets.length. And the third thing is what to do after each iteration. And we're just going to say I equals I plus 1, or we could just say I plus plus and get the same thing. Now we can simply output the value by saying console.log planets sub I. Saving this, you can see the three values listed on the right. The next type of for loop to look at is the for of loop. So instead of explicitly creating an I to iterate through, we would just say for, and then in parentheses, and now we can say const instead of let, because this value is not going to change as the loop iterates. And we're just going to say planet of planets. Again, curly braces for the statement. And now when we log the planet, we can just say planet without any sort of indexer because we declared it just const planet. And now this is going to give us each individual object. Again, Mercury, Venus, and Earth. The last of the for loops we're going to be looking at is the for in. So this doesn't work so well for an array. It works really well when you have an object with keys and values. So let's grab from our planetData.js just one value, Earth data. Copy that back to our test.js. Now we can iterate over the properties in Earth data. That's just simply for const property in Earth data. And if we output property, we can say console.log property. But what's convenient about this is we can say Earth data and give it the indexer of property. And now when we save that, we get all the properties starting with name, then color, radius, distance, angle, and angle change rate. This is really helpful when you want to interrogate a JavaScript object. Now that we have the basics of for of, and for in under our belts, let's look at while and do while. Let's use our planets array that we created earlier and get rid of everything else. The simplest while loop I can think of is this. We just simply say let I equals 0. Then we say while I is less than the length of the planets array. That's just planets.length. Then we output the individual planet. That's just console.log planets sub I. And then we increment I. Saving this, we get our 3 planets in order as expected. There are a couple wrinkles to while. For one, there's this break that you can insert in there. So for example, I could say if I is greater than 0, then break. Saving this, all we get is Mercury because after the first iteration, break breaks us out of the while loop and ends processing. Let's remove that break now. The other interesting thing we have in a while loop is the continue statement. Continue basically says when you hit a continue statement, stop executing what's in the statement group. In this case, that would be our console log in our I++, and then continue the iteration as normal. So in this case, we could say if I equals 1, we'll increment the loop like normal. but then we'll say continue, which means that the console log should not get output. Executing that code, you can see that we get Mercury and Earth output, but not Venus as expected. Both continue and break are really from the old school of how to program. The idea in general in programming is you don't want to just break out of loops. You want to have some sort of conditional in the loop itself, if you're going to use a while loop, to stop that processing, but not somewhere in the middle, just jump out and hope you can figure it out later. I avoid break and continue as much as I can. Besides while, we also have do while, which is practically the same. Let's take a look at that for the same problem. Let's comment out our while loop and write a do while in its place. That would simply be do, then we output our planet's entry, console.log, planets sub I, do our increment, I++, and then after our closing, we simply say while I is less than planet.length. Saving that, we get our result just like before, Mercury, Venus, and Earth. Everything I said regarding break and continue applies to this. We could do exactly the same way. And just like I said before, I don't recommend using either of those unless you absolutely have to, or the code came with it and you just have to live with it. Let's now talk about a functional way of iterating over arrays. So let's comment out all of our do while and whiles. And now over our planets array, let's use forEach. The way forEach works is off of arrays, planets in this case, we can type forEach in camel case, and then we pass into forEach a function that gets called for each element in the array. That would simply be function, planet, and then console.log, planet. Saving that, we get exactly the same result. The benefit of this is we can refactor this code by selecting what's passed in, the function in the first parameter, and instead of having it as what we call an anonymous function because it doesn't have a name, we can replace that with something like this, where we simply write a function called output planet, and then declare that function. Something simple like function output planet. It receives a single parameter, just like before. And then when we console log, we get exactly the same thing. Let's comment this out also, and then talk about the map function. Map is very similar to forEach in that we can say planets.map, pass a function in exactly like we did with forEach. Console log the output, and we get exactly the same result. What's different about map is it can return a new array. So for example, if we were to simply say return planet, then we could say const new planets equals, and then when we console log new planets, we get a new array that has the same entries as the original ones. What's really nice about this is that you can modify the return to be something different. For example, say if the return is Earth, we could return that as uppercase, just return Earth, else do the default behavior. Now you can see in the return, Earth is uppercased as we would have expected. What's also nice is the parameters passed to the function also include the index and the original array. If for some reason you wanted the index, you could append to Earth. You can see Earth now has the number 2 alongside it. That's very convenient when you're working with arrays. Let's now go back to our solar system app and replace our for of loop in our drawStar.js to forEach because basically it's the same thing. It's a functional approach which I personally like better, but ultimately it does the same thing. Let's also, while we're here, add all the other planets to our solar system. To do that, we go into the planetdata.js file, and below Venus data, let me paste in all the other planets, starting with Mars, then Jupiter, then Saturn, Uranus, and Neptune. Navigating to app.js, let's remove how we added Mars as a single planet using the spread operator. At the top, let's add the other imports for the other planet data. That's just Mars data, Jupiter data, Saturn data, Uranus data, and Neptune data. Now, in our planets array, add that same list. And in our sun data, go back to just the standard reference planets using the ECMAScript 6 shortcut. Back to our drawStar, we can replace our for loop with just a forEach by typing planets.forEach, and then create the anonymous function which takes planet as its first parameter, and copy the meat or the statement portion of our for of loop into the anonymous function, and delete what's left of the for of loop. One thing to notice now, though, is in our browser, we do see Mars, but it looks like our planet scaled off the page. Coming up in the next module, we'll write some functionality using operators to scale this correctly so it fits on our page. For now, though, let's create a little shortcut. Let's create a new constant scale factor. And I happen to know 0.32 works quite well, so let's set it to that. Then from the planet distance from our star, let's multiply that distance by our scale factor. For consistency, we can also do it for the planet Y, even though 0 times the scale factor is still going to be 0. Of course, we also have to do it for the orbits. Now, saving our file, we can see all 8 planets in the solar system. That basically concludes converting our loop to a forEach. Just a side note, we didn't convert it to map because we weren't using what was returned from map, which is the correct way to use forEach. That is, only use map when you're going to use what's returned from the map function. Coming up, we're going to talk about comparison and logical operators. I basically divide this up into 4 areas. Those would be things like equals and not equals, strict equals and strict not equals, which includes a type comparison too, greater than or equal to, less than, and less than or equal to. The next group are the logical operators. Those are typically when you have the comparison operators like equals to, but you have multiple of those and you have to say if A equals B and C equals D. So those are basically logical and, logical or, and just plain not. The third group is kind of a miscellaneous group. The first is grouping. That's just parentheses, which are used for ordering in precedence, like star for multiply has a higher precedence than plus. Nullish is used for things like comparisons where you may have a number that might be null. You can use nullish to force it to be something like 0 if that's your default. The string plus is used to concatenate strings together, like first name plus last name. Ternary is a conditional which really replaces an if-else, but it's a convenient way to do it in one statement. And relational in is a way to iterate through properties in a JavaScript object. Then we'll talk about the 2 ways to do conditional statements. One is if, then, and else, and the other is the switch statement. They basically do the same thing. though switch can be cleaner for certain circumstances, but it's your preference. At the end of this module, we'll have a short section where we'll upgrade our solar system map to spread the planets out a little better using some of these operators in examples. Let's start out by going through the basic comparison operators. Those are the equals and the less thans and greater than type operators. We're here in Visual Studio Code, just like we've done before in our simple test.js file that gets rendered from test.html, and the output is rendered on the right in the console log. For simplicity, let's get rid of everything but the planets array in this file. One convenient way to look at the results of a comparison operation is to simply console log that result. So I'm going to say console.log, and then I'm going to say something that's obviously not true. 1 equals 2. And if I save that, sure enough on the right, it says false. If I change that to 1 equals 1, that's true. That makes sense. What equals does is it compares what's on the left side with what's on the right side. And if they're the same, the result is true. The fact that it's equals means that it also compares the type. So for example, if I made that a 1 in quotes, it's going to be false, because even though 1 does equal 1, if there weren't a type involved, the fact there is a type involved, we're comparing a number with a string, then it doesn't equal. However, that leads us to the standard equals, and that is true. Equals basically means ignore the type and make the comparison. Analogous to equals is simply not equals. Does 1 not equal 1? That's false, because it does equal. What about not equals? It's going to be true because 1 actually does not equal, quote, 1, quote. The greater than and less than comparisons are also very straightforward. If I say 1 is greater than 2 and save that, it's false because 1 is not greater than 2. If I say is 1 is less than 2 and save that, that is true. If I say is 1 less than or equal to 2, I'd say that's true. How about 3 less than or equal to 2? False. And the same thing with greater than. Is 3 greater than 2? Yes, it is. True. Is it greater than or equal to 2? That's also true. Basically, those are our standard comparison operators. Very straightforward. The thing to always be careful of is making sure if you're using the strict equals, that your types are correct and the same. Let's go through and do a couple simple examples of ands and ors. Following the same plan as last time, let's console.log the output, and let's ask the question, is 1 equals to 1? And then we'll use the double ampersand, that's the and operator, 2 equals 2. So what this is saying is 1 equal to 1 and is 2 equal to 2. Well, the answer is yes, it is. So if I save that, sure enough, it's true. How about if I say is 1 equal to 2 and is 2 equal to 2? Well, no. Both of them have to be equal for the and sign to evaluate the full expression as true. So that's going to be false. The trickiest thing always to remember is if you're using the double equals, pay attention to the type of how it evaluates. So if I say is 1 equals 1 in quotes, this is going to be false again because the expression on the left side did not evaluate to true. Another way to think about it is you can simply say true, and that's going to evaluate to true. If either of these are false, or both of them are false, the expression is going to evaluate to false. So let's look at the OR operator. The OR operator is 2 pipe signs. If either of these is true, then the expression is going to evaluate to true. But in this case, false or false? No, still false. If I make one side true, yep, true. If I make both sides true, same thing. Either one is true, then the expression is going to be true. The final thing to talk about is not. Not is really easy. It just toggles the value of the full expression. So for example, if I were to say is not true or true, well, the left side is going to evaluate to false. The right side is going to be true. So if I save that, well, or makes it true. If I were to change this to and, that's going to be false because the left side does not evaluate to true. That's basically it for logical comparisons. Let's talk about some of the miscellaneous operators that will come up a lot in your JavaScript programming. Grouping that's using parens is certainly a big one. Say, for example, you have three constants, const A equals 100, const B equals 150, and const C equals 1000. If you were to console.log the result of A plus B times C, you'd get 150,100. And that's because B times C takes precedent over A plus B. Say you wanted A plus B to take precedence, you would use the parentheses, and now the answer is 250,000. So parens are very important. Another example is with logical operators. Like before, if we said console.log false and true or true, and render that, we get true. But if we put parens around the or, the answer changes to false. That's because and takes precedent over or, but that's really hard to remember. So I strongly suggest you always use parens and not rely on the precedence of the operators. Another operator to look at is what we call the nullish operator or question mark. What that does is say you have a variable that you've defined with let, like I'll say let name equals Peter. Then when I console log that, I get Peter as expected. Well, what happens if I assign that nullish coalescing operator to it and say not defined? If I save that, I still get the same thing. Well, what if I just don't bother to define it at all, which is completely valid? I get the not defined error out of the console.log. What if I said let name equals null? Well, same thing. How about just a single quoted string? That actually is a value. It's an empty string, so nothing is output, but certainly not defined is not output either. The next thing to look at is the plus operator. Say we say const first equals Peter and const last equals Kellner. Now, when I console log first plus last, I get Peter Kellner, but there's no space in there, so I could actually just add another space with another plus, and now I get Peter Kellner spaced correctly. Ternary operators, just the single question mark, are also very useful. Though we'll look at if-then-else statements next, a ternary operator basically gives us a really quick way to do an if-then-else. For example, we could say let I equals 100, and we could say console.log. We could say if I equals 100, then question mark, that's the ternary operator, we could say console.log I is 100, and then we use the colon, which basically says if it's false, we can say console.log I is not 100. Saving that, it says I is 100. If we were to change that to 101, I is not 100. So that's the ternary operator. The last useful operator that we want to look at is the in operator. You might think that in my planets array, I could say console.log, and I could say Earth in planets. And you might actually think that would return true because Earth is in planets. Well, that's actually not how it works, so I'm not even going to leave this code here. What in does is it only looks at objects. So let's go over to our planetdata.js. Let's grab our Earth data object, come back to test, paste it in here. We can say console.log name in Earth data. And now that's true. If we misspelled name X, it would be false. So the in operator basically lets us interrogate an object and see if a property exists in that object. That can be very useful when you have dynamic properties associated with objects, and maybe it was assigned to it, maybe it wasn't. Let's now talk about two different types of statements or declarations. One is if-else, and the other is the switch statement. They are similar, yet sometimes one is better than the other, and vice versa. So let's start out with the if-else. We're back in our test.js where we've been doing our sample simple code. Let's get rid of everything but the planets. Let's make an example of an if-else statement using animal types as an example. Let's assume we have two different animal types we want to sort out. We want to know if a poodle is a dog or a cat, and we want to know if a Siamese is a dog or a cat, and then output the proper answer. Doing that with an if-else would look like this. We'd start out declaring the animal type that we want to check. That might be animal type equals poodle. Now let's check and see if it's a dog or a cat. We would say if animal type equals poodle, then console.log, this is a dog. Then we would say else if animal type equals Siamese, we would say this is a cat. If it's neither of these, we would say this is not a dog or a cat. So if we run this and we look at our console output, it says this is a dog. If we spell poodle wrong, it says this is not a dog or a cat. And if we replace it with Siamese, this is a cat. So that worked. Let's do the same thing with the switch statement. The syntax for a switch statement is just this. You say switch, then in parentheses you put what you want to switch on, which in our case is animal type. Then for each animal type, you define a case. So I would say case, poodle, then a colon, and then if this case matches, I simply do the same console.log. This is a dog. And the next line is important. I want to say break, which means don't check any more cases. For the next case, I want to say case Siamese. Same thing. Console.log. This is a cat. Break again, so we don't continue processing. And then the equivalent of the else is default. That basically says no other cases were hit. So console.log, this is not a dog or a cat. So both times the if and the else if recognize the Siamese as a cat, put in poodle. They both recognize poodle as a dog, spell poodle wrong, and both of them recognize this is not a dog or a cat. So I would say in this case one isn't harder or easier. But what if we have multiple different animal types that we want to compare? Let's say we want to check for a beagle in addition to a poodle, and if it's either one, we want to say it's type dog. After the animal type equals poodle, add or animal type equals beagle. Then we're now checking for beagle or poodle. So if I change that to beagle, The if else says it's a dog, but we haven't updated our case statement yet. So let's do that. In this case, all we have to do is add another case, Beagle, and we don't have to add anything else. The reason is, once a case is matched, any statement below that is executed until a break is reached. I won't go on continuing to add multiple different dog types and cat types, but you can imagine that after you've added several, the if-else if is going to start looking really complicated with all the ors, and the case statement is going to stay pretty clean. In this particular case, if you just had one or two dogs or cats, I'd say if else is good. If you have a lot of dogs and cats, a case statement is better. And if you have a whole lot of dogs and cats, I'd suggest moving to an array to hold the dogs and cats, and then check the array to see if the appropriate one is in it. I'd probably use an if else to solve that with a little bit of logic in each condition to check the animal type. Previously, when we drew our solar system with the 8 planets, we guessed at a scale factor of 0.32 so that we could fit all of our 8 planets in there. But say we wanted to have that automatically figured out rather than have it passed in just simply here as a constant. So let's start out by getting rid of the scale factor here, and let's have it passed in as a property on our sun data, just like we passed in planets. So I'll just add scale factor, and we'll assume that we have that correctly now. So let's go back to app.js, and for now, just to have it work exactly the same, let's add it as a passed-in property in SunData. So that would just be scale factor 0.32, and that's exactly the same as we had before. Now though, let's use some of the knowledge we gained earlier with our looping statements, as well as some of our comparison operators, to figure out what the actual scale factor should be. We'll do that first by finding the maximum distance any planet is from the sun, and then we'll just do a little conversion based on the width of our canvas to figure out what the scale factor should be. Since we have our planets array already, remember that gets data from planetdata.js. Each planet has a dist in it. Notice Earth is 110, Mercury is 59, Venus data is 90, etc. What we can do is we can map over our planets starting with a max distance of 0 and figure out a new max distance for any planet. We happen to know that the last one is the furthest away, but let's just pretend we don't know that. So here's our code. We start out by saying let max distance showing equals 0. Then we just iterate over all our planets. We say planets.forEach function, and we give it a parameter of just planet data. We say if max distance showing is less than planetdata.dist. If that's the case, then we set a new max distance showing to what that value is. Now, when forEach completes, max distance showing is the largest dist in the planets array. Lastly, now we can calculate our scale factor. That's going to simply be const scale factor equals, and then using the grouping, we'll say canvas.width minus 100. That gives us a little bit of a buffer over our 100 wide canvas. And we'll divide that by max distance showing. And since max distance showing is actually a radius, we'll multiply that by 2 because that's the actual width. Now we can replace our scale factor of 0.32 with the actual scale factor. And notice now the property name and the value is the same, so we can use the ECMAScript shortcut to get rid of that. And now we have our new calculation. So for example, if we were to simply say our planets ended at Earth, and then comment out the second line, notice our result scales exactly like we would have expected. Let's put our planets back in, and we're back to the correct size. One last thing we can do to make this a little bit better is let's spread our planets across both the left and the right side of our solar system. We can do that by going into Draw Star, and let's think about how we could make every even planet automatically be on the other side of the solar system. Well, we have a planets.forEach, and if you remember, the second parameter that gets passed into the function in forEach is actually the index. So if we add that, we can know that it's 0, 1, 2, all the way up to 7 for the 8 planets. So let's start out by using our remainder operator to figure out if the index is even. So how about if we just say const is even equals index remainder 2 equals 0. Now, if is even is true, we want the planet on the right side of the solar system. If it's not true, we want it on the left. An easy way to do that is just add another expression after the star 1 to say multiply by if is even, and then using a ternary expression, we can say 1, meaning multiply it by 1 if it's even. If it's odd, multiply by -1. And of course, we have to add the multiplier operator again because we're multiplying by a scale factor. Saving this, you can now see we have our even planets on the right and our odd planets on the left. This is much nicer. Let's talk about one final thing in this module, and that is let's take advantage of the JavaScript spread operator and the math max function to optimize this code where we loop through the planets to find the max distance showing. Let's do this first by commenting out the forEach where we calculated the max distance showing. That will give us something to look at while we're refactoring that code. Since we're going to do it all in one line, we don't need let anymore. We can just say const, and let's replace the equals 0 with what we want for the result. Earlier in the course, we talked about the JavaScript library functions under math, so let's use one called max. That's simply math.max. And then in parens, we give it a list of variables, and we want the maximum one returned. One convenient way to do this is to use the spread operator and the mapping function. First, we use the spread operator to spread the planets array. Then, since those are JavaScript objects, we really only want the max distance value, which is just dist, so we call map, giving map a function that takes a single parameter we'll call PL, that's a single planet, and then what we return from that is going to be the value that math.max looks at. In other words, we're going to say return pl.dist. Now, when we save that, we have exactly the same thing as we had below when we did the forEach and we did the manual comparison of max distance showing to planetData.distance. It's probably not any faster, but it is a little bit more clean when I look at it. Our plan for this module is to talk about how JavaScript variables are declared and the different scopes they have access to. Scope in JavaScript basically determines where you have access to variables. That is, if you declare them outside a function, can you access them inside a function, and things like that. In JavaScript, there are 3 different types of scope: block, function, and global. Closure is actually one of the more advanced JavaScript features, but once you understand scope, it's pretty clear how it works. In this module, our plan is to set our solar system planets in motion, taking advantage of how to use functional scope which goes directly towards closure, and we'll use that to track our planets in motion. Let's start out in Visual Studio Code in our test.js file, which is called from our test.html, and as you see here is running in the browser on the right with a console log at the bottom. As usual, let's remove everything in this file except for our planets declaration, and let's start talking about scope. You've seen in things like if statements, I could say something like if planets.length is greater than 3, then do something. Well, the then do something with the curly braces is actually creating a block scope. If, for example, I were to declare a variable like this, const abc equals 100, and then, of course, I can say console.log abc, then if the length were greater than 3, I would see that, but it's not. So let me change that length to greater than 2, which it is, and now we see our 100. What happens if I move this console log down to below the curly braces and save it? Well, I get an uncaught reference because ABC is not defined. The reason it can't find it is because const ABC is in what we call block scope with the curly braces. Getting an error when accessing the data outside of those curly braces means it's not able to find it. How about if I change that to let? Will that work the same? Yes, it does. It can't find it. What about var? If I say var, will that work? Well, it actually does. So var does not work in block scope. The reason is block scope didn't exist before ECMAScript 6, and in ECMAScript 6, you didn't have let in const, only var, and var basically made the variable a variable in what we call functional scope. Let's change our var back to const, and for now let's remove the console.log just as a starting point. So functional scope basically means the curly braces inside a function declaration. So for example, if I wanted to put all this code inside a function, I would say function myfunc. For now, I'll give it no parameters, open curly brace, close curly brace. And then for testing, I'm going to call that myfunc with open close. Just by way of testing, if I say console.log abc, save that, of course it doesn't work because abc is in block scope, which in addition is now in function scope, but in any case, it's not in the scope we have outside here, which is actually called our global scope. It's not inside a function. What about if we change this to var? Same thing. Function scope existed before ECMAScript 6, so var doesn't actually help us there. So let's change that back to const. And also, let's get rid of the if statement now, since we're really just talking about functional scope, and we don't want to confuse things. How about in global scope if we said const abc equals 200? Now it's going to show 200 because even though myfunc declared it in local scope, that really didn't affect our global scope. How about if we move this console log inside our function? Saving that, now it's 100 because ABC in the functional scope is overridden in the functional scope from whatever was in the global scope before. So does this look like a good practice? It absolutely is not. You should try really hard to never override variables if you absolutely can, so that you don't get results like this, which would potentially be confusing. What if we wanted to get back that 100 from our call to myfunc? Well, we could put the console.log back below myfunc again, and then in myfunc we could just say return abc constant abc equals myfunc, and of course we want to remove it from our global context up there. Now when we save it, we get the 100 because we referenced it from a return, which is how we can get variables out of function scope to the caller, which in this case is global scope, but it could just as well have been another function calling it. That basically covers block scope, function scope, and global scope. The next thing to do is to introduce closure. Let me explain by example rather than try to give you a complicated definition of what closure means. Say, instead of calling myfunc and having it return ABC, instead we want to get a reference to myfunc and then return a method from myfunc that will let us get the information back that we want. Instead of returning ABC, let's return a function, and let's call it log ABC, and assign to that an anonymous function. We'll just say function, and have that return ABC. Now, instead of having myfunc return ABC, which is the result of ABC equals 100, let's return something, and we'll just call it props for no particular reason. Then we can get a handle to that function by saying const log ABC equals props dot log ABC. Now, instead of calling console log ABC, we'll just call log ABC, and then we'll execute that. Saving this, we get exactly the same result. We get 100 return. Just to prove it, change that to 101, and we get 101. We can shorten this a little bit. Instead of doing this in 2 lines, we can change const props equals myfunc to just destructure it and return log ABC, and then we no longer need that line of code. So what's different about this than what we did before? Well, essentially, the return from myfunc is a function. Because we now have a reference to that function, that means that const ABC equals 101 still lives in functional scope for myfunc. So what's the implication of that? Well, the implication is we could return another function, and I'm just going to call it increment ABC, again an anonymous function, and instead of having it return something, I'm going to have it increment ABC. That is, I'm going to have it say ABC equals ABC plus 1, or I could just say ABC plus plus and get the same thing. We know now that because we're incrementing ABC, we have to change our const definition to a let. Now we need to add to the return of myfunc increment ABC. After we log ABC the first time, let's call and execute increment ABC. And then console log ABC again. And now in the console window, you can see first 101 is logged, then after the increment, 102 logs. If we do these lines of code again, simply increment ABC, and then console log the result, saving that. Now it's 103. So what's happened here? Essentially, we've kept ABC in functional scope inside myfunc, and then from outside, we called a function that incremented that internal value. And so that's how it went from 101 to 102 to 103. Then after each increment, we logged it to show that internal value changed. That's exactly what closure is. The technical way to say that is we're storing ABC in closure for the function myfunc. You'll see coming up how in our solar system app, we'll store the position of each planet in closure with a new planet object. Then, as time moves forward, we'll call an increment function that moves each planet the right amount around our solar system. If you were able to follow the previous clip where we implemented closure, you're doing great. Typically, closure is not thought of as something that would be in a beginner's JavaScript course. I feel strongly, though, that it's a very important feature of JavaScript, and if you understand it, that means you really understand scoping in JavaScript, which is equally important to understand. If you don't, I'm sure you will over time. and you can always come back and rewatch this module. Coming up now, we're going to implement closure in our solar system app, and it's going to be a little more than 20 lines of code to make it work. So again, don't be frustrated if you can't follow exactly, as I'm sure over time you will figure it out and it will look natural. As our goal is to set our planets in motion, there are a number of things we have to do to make that happen, including taking advantage of closure. Let's strategize how we're going to do that in our current solar system app. We're here looking at our planetdata.js, and notice that we have our angle, that's where our planet is meant to start, and our angle change rate, which is on every increment. We don't actually know what that increment is, but assume it's something like a day. Our planet's going to move that many radians. Remember, 3.1415 radians is 180 degrees, or half an orbit. Each planet has both an angle and an angle change rate. So let's go back to our app.js file and talk about what our plan is. Currently, we call drawStar with our canvas context, that's just context, and we pass it sun data, which simply includes the information about our sun as well as the 8 planets in their positions. What we plan on changing is instead of passing the 8 planets with their raw data, we're going to pass a planet object to our drawStar, and then drawStar is going to remember where each planet is and move each planet the number of radians in angular change rate. That is, we're going to call drawStar over and over and over, and each time we call drawStar, the planets are going to move that number of radians. The way this is going to work, each planet is going to remember in closure where its last position was. The idea being that if we continually call drawStar over and over and over, the planets will just slowly rotate around the sun. Let's get started with that plan. To help us prepare for setting our planets in motion, let's move the scaling of the distance between the sun and each planet into the planets array before we call drawPlanet. So the first thing is, remember the way we set our scale factor to make our solar system fit in our canvas is we calculated the maximum distance of any planet from the sun, then we calculated a scale factor by comparing the canvas width to that maximum distance and coming up with a nice ratio. We then passed in our sun data that scale factor, and then when we called drawStar, we used that scale factor to calculate the distance between each planet and the sun. Let's now, instead of changing the planet distance to each star as we draw each star, let's create the scale factor in our main app, scale our planets array, and then we don't have to do that in this drawStar function. So first, we remove the scale factor from our sun data properties passed in. Then, since our plan now is to show the planets in motion, we don't need to do the is-even thing where we put some planets on the left and some planets on the right. So let's remove index from our function call and also the const is-even. And then for planet X, remove all those calculations that included the scale factor and the positioning. Since at the moment all the planets are at the same level as the sun, we can just say planet Y equals Y star. With drawOrbit, we can do the same thing. We can just plain remove the scale factor. You can see now in our browser we don't have any scaling, and everything beyond Mars is basically off the screen. Now that we've simplified our drawStar not to do any scaling, let's go back to our app.js and do the scaling there. Below where we calculate our scale factor, we just simply need to iterate over all our planets and update our planets data array such that the distance from the sun for each planet is the appropriate distance based on the scale factor. Remember, in our planetdata.js, Each variable, Earth data, Mercury data, Venus, etc., we have dist as a property. So what we want to do is multiply that dist by our scale factor. Back in app.js, we need to iterate over our planets array. The way we'll do this is we'll use map and return a new array with those values updated. So that simply becomes const planet data. That will be our new array, and we'll say equals planets.map. We pass map a function that takes a single parameter, planet, and then we want to return from that a new planet with the distance updated. Something we've not done yet is updated a JavaScript object for a single property. Let's do that now with the spread operator. If we simply said ... planet, that would simply make a copy of our planets into planets data. Then all we'd have to do in our sun data declaration is change our planets declaration, which is now using the ECMAScript 6 shortcut, to just essentially say planets::planets. That's what we have now. We just change that to planets data, and essentially nothing would change. However, what we do want to do is with the spread operator, we want to first spread all the properties from planets, and then we want to replace just one of them, dist for distance. Then we say dist::, and then we take the original planet.dist and we multiply that by the scale factor. Now, when we save our file, our solar system goes back to scaling correctly. Let's also remove our scale factor from our sun data as we're no longer using it in drawPlanet. We now have our drawStar and app.js files updated so that scale factor is now baked in to the planets array rather than calculated on the fly as we draw each planet. This will be helpful when we set our planets in motion coming up. Let's now take advantage of functional closure and move our planets' information, including their position around the solar system, into a local function. Let's do that by creating a planet function for each individual planet, and then in that function include in closure the location of each planet, that is the X and the Y location relative to the sun for each planet. We'll do that by, instead of calling drawStar with sun data that has an array of planets data associated with it, we'll instead call drawStar with the same sun data object, but the planets will be an array of functions. That way, each planet will maintain its own position rotating around the sun. Let's assume we have a planet function created already, and then we'll create a new array of those planet functions by iterating over all our existing planets. In other words, we'll create a new array called planet functions. To create that, we'll map over all our existing planets. The way we do that is we simply return from the function passed into map an instantiation of planet function with the sun position, the planet data itself, and we'll pass in the context so the planet function has the capability of actually drawing itself to the canvas. Let's also update the planets property associated with sun data to planet functions. This now gives drawStar the functions associated with each planet instead of just the planet's data. Let's scroll to the top and then import planet function as if we already created it. Now, let's create that file. Just simply planet function.js. Rather than code this from scratch, let's take a look in our test.js where we recently created myfunc, which we used to create a simple variable enclosure and then exported a simple function increment abc to change that variable. let's copy the function itself from here and paste it into the planetfunction.js. Before making any changes, let's look at one particular feature of JavaScript functions. That is, say we wanted to pass in the initial value of ABC. We could add that as a single parameter to myfunc, just ABC, and then we could remove let ABC equals 101. Essentially, ABC is passed in, and that becomes a local variable to myfunc. Since that's a local variable, we can update that just like any other local variable. And it's maintained in closure. Now let's make our changes. Let's rename myfunc to planetfunction. Then, for the passed-in parameters, we create the ones that we passed in app.js moments ago. That's just sun position, planet data, and context. To make our life simpler, let's destructure those on the way in. Sun position just becomes x, and further destructuring, or basically renaming, we say sunx, and y becomes suny. For planet data, we say name, color, radius, dist, angle, and angle change rate, and context just stays context. Now, for our function returns, let's rename logabc to drawPlanet. Let's add another function, drawPlanetOrbit, and let's rename increment ABC to just simply update. The idea now is that our planet function has the ability to draw the planet itself. It has the ability to draw the orbit, that's the 360-degree circle around the sun, and it also has the ability to update those planet positions. We've now got our planet function pretty much stubbed out. All that's left to do is to implement drawPlanet, drawPlanetOrbit, and update, and also include the code in drawPlanet that calls these functions as necessary. That's coming up. Here in our planet function, we have the three methods, drawPlanet, drawPlanetOrbit, and update. We've never called them, so let's go back to drawStar and look at the forEach loop that we have that iterates through all the planets. In this function, we're essentially calculating the planet X position, the planet Y position, and then we're drawing the planet. So let's copy that code, navigate back to our planet function, and put it in drawPlanet directly. Since drawPlanet is all about drawing our solar system, not just a generic star, we change the X star reference to our Sun X reference and Y star to our Sun Y reference. Also, because we're no longer iterating through an array, our planet properties are just passed in directly, so we can eliminate the prefix from each reference. Similarly, for drawOrbit, back to drawStar, pick up the drawOrbit call in our planets forEach, back to planet function, put that back in drawPlanetOrbit, X star goes to Sun X, Y star goes to Sun Y, and planet.dist simply becomes dist. For now, in update, let's just leave that method empty. We'll come back to that momentarily. Since we are going to use planet function externally, that is from app.js, we do need to export it. Also, since we're now referencing drawOrbit and drawSpaceObject, we do need to import those at the top. Now that we have our planet function completely built out, that contains our planet positions in closure along with the methods to draw the planets, the orbits, and update those positions, we need to go back into app.js where we previously calculated the planet positions and instead called this function in its place. Heading back to app.js and scrolling down to draw star, notice now planets is planet functions in our sun data. So when we go to draw star, our array we receive into draw star is now planet functions. Likewise, we're iterating over planet functions, and each one becomes a planet function. And now in our array, we call planet function drawPlanet. So we're calling that method inside of planet function. The same for drawPlanetOrbit. That's just planet function dot drawPlanetOrbit. And let's also call update, even though at the moment update doesn't do anything, but eventually that will move our planets around the orbit. DrawStar's functionality is now basically the same as it was before, but instead of calling static functions, we're calling functions return from functions to take advantage of closure in functions. Navigating now back to app.js. For convenience, let's rename our planets in SunData to simply planet functions, so that way we're not confused and we don't think that planet is really data. It actually is planet functions. And of course, using the ECMAScript syntax for shortening property references, we can just call that planet functions. And as should be no surprise, our solar system is drawing all the planets as expected. We're now finally ready to set our planets in motion. But first, just a quick review of what's happening in our app. We're here in app.js, that's essentially our main procedure, and at the bottom we simply clear the screen and then we draw star, which draws to our canvas this SunData object. That SunData object includes information about the sun, and it includes an array of planet functions. Each of those planet functions was created to include the current sun position, the data associated with the planet, and a context which gives the function the ability to write to the canvas or the HTML page. The function itself doesn't actually write to the HTML page. Instead, it returns 3 functions which give you the capability to write to that HTML page by being called externally. One to draw the planet, one to draw the planet's orbit, and one to update the position of the planet. Let's now enhance this planet function such that instead of drawing the planets basically along a horizontal line at the same level as the sun, to instead draw the planets at different positions based on the angle passed in as a parameter as part of the planet data. The idea is that we'll calculate the planet's x and y based on that angle. To start, instead of declaring planet x and y at the top of our function, let's instead make those constants as part of drawPlanet. That way, they'll get calculated when drawPlanet is called, and that calculation will be used to draw the planet. At the moment, the angle passed in doesn't have any effect on where the planet is drawn. So let's change that by simply calculating x based on the distance from the sun times the sine of the angle. Let's do something similar with y, where we add the distance again, but this time we multiply it by the cosine of the angle. That way, instead of the planets being lined up like this, they'll be wherever the passed-in starting angle is. Speaking of that starting angle, where does that come from? Well, it was passed in as part of the planet data, which if we look in our planet data itself, that's always math.pi divided by 2, which is why our planets are always along the same horizontal line. Let's change that value from math.pi divided by 2 to instead math.random that returns us a number between 0 and 1, actually inclusive of 0, but not 1. And then let's multiply that by 20 so we get something reasonable. We could do this for all of our 8 planets in planetdata.js, but we know a better way to do it. Let's reset this back to the default, which is math.pi/2, and navigate to our original app.js file. In the same calculation where we updated our distance from the sun to each planet, we can also add that random calculation here. We could simply say angle :math.random *20. Now, when we're recreating our planet's data array from planets, we not only have the scale distance, but we have also a random starting angle. Saving our JavaScript, sure enough, the planets now are spread out in their orbits randomly. Refreshing the page over and over again. Each time we refresh, app.js reruns, and a new random position is calculated. Not astrologically accurate, but much more interesting. To set our planets in motion is actually very simple at this point. Let's navigate to app.js and talk about that. What we want to do is add some code to our update method that gets called each time drawStar is executed. Then in app.js, we can take clear and drawStar and execute that over and over again, and that will essentially move our planets. Let's create that repeated execution first. We can use the JavaScript setInterval function, which takes multiple parameters, the first two being the function, and in that function, we're going to do our clear and drawStar, and the second is the number of milliseconds to repeat it after. I'm just going to say 20. Remember, in drawStar, we call planetFunction.update each time drawStar is called, so that's going to be 50 times a second. Then if we go into planetFunction, currently update's doing nothing, but since angle is passed in, and that's in our local functional scope, which means we can update it and keep that value in closure, all we need to do is increase it by angle change rate. That's simply angle equals angle plus angle change rate. Now, every time update is called, the angle is going to increase by angle change rate. And if you remember in planet data, the angle change rate is different depending on which planet we're on. Saving this file, all of a sudden we notice the planets are moving as we had expected. If you've successfully followed along until now, congratulations! Closure and moving our planets around the sun is probably a little more than beginner JavaScript programming, but it follows the simple principles of JavaScript, and with a little bit of functional programming, it's pretty straightforward to follow. Before moving on to the next thing, let's stop these planets from rotating around the sun, as it's going to drive at least me crazy, and I'm guessing you also. We'll start them again at the end of the section. So here's another chance to stretch your thinking. Let's rotate some moons around both the Earth and Mars as those planets are rotating around the sun. If you followed the principles that we've built with so far, this is going to be very straightforward and surprisingly not that much code. Let's start out by going into our planetdata.js file and let's add those moons directly to our raw data. To Earth, let's add a MoonData list property and assign it an array with one object, and that's our one moon. The properties are name, we'll give it a blank name for now. Color, let's make all our moons white. Radius, make that 1.0, that's the radius of the moon. Distance, that's the distance from the Earth to the moon, make that 10. Angle, that's the starting angle, make that 0. And angle change rate, make that the same as the Earth, but multiply by 12. As the moon revolves around the Earth, 12 times in a given rotation of the Earth around the Sun. Let's scroll down to Mars. Same property, moon, data list, and make it an array, but Mars has 2 moons. So let's create those 2 moons as 2 separate objects in our array. We'll assign the name blank, make the color white, make this radius 1. Let's make the distance from Mars 5. That's pretty close to Mars. The starting angle 0. And the angle change rate, same as Mars goes around the Sun, times 30, as this moon really zips around the Sun. The second moon, name blank again, color white, radius 1, distance to Mars 9, make this a little further away from Mars, starting angle 0, and the angle change rate, same 0.006 as Mars goes around the Sun, but this one times 45, even more zippier than the first moon. That gives us all the moon data that we need for the planets that we want to rotate moons around. Coming up next, we'll set those moons in rotation. Let's now add the capability to our JavaScript app to rotate our moons around our planets. Like before, we had a planet function that tracked the angle the planet was relative to the solar system. Let's take that same code and create a moon function. And as a starting point, bring in the same code. We are still going to need to draw a space object, so let's keep that, but we're not going to draw an orbit for the moon, so remove that. We don't care about the sun position because now all we're tracking is the motion of the moon, but instead, to draw a planet, let's pass in the parameters planet X and planet Y. That way we'll draw our moon based on wherever the planet currently is. Change the position we're calculating for planet X to moon X, change the base position to planet X, and do the same thing for planet Y, and update drawSpaceOrbit to point at moon X and moon Y. The only other change is to remove the function drawPlanetOrbit. Now, since the moons are rotating around the planets, let's go into our planet function, then add to our passed-in values for each planet the MoonData list. When our function is first initialized, that is, when the planet function is created, let's create an array of moon functions associated with the moons for the particular planet. That is, let's create a ternary expression that checks for the existence of MoonData list. Then we map over MoonData list, returning from that function passed in a new moon function, which gets each moon along with the context so the moon can be output to the canvas. If MoonData list doesn't exist, then we just return an empty array. Of course, we also have to import moon function at the top of our file. The next change to our planet function is we want to update the returned drawPlanet function. Currently, it draws the planet based on what the current angle is of the planet around our sun. After we've calculated the position of that planet, we then want to draw all the moons around that planet. We can do that by, after our drawSpace object, which draws the planet, we can do a forEach on the moon functions array. Then, for each moon function, we can call drawMoon, passing in the current position of the planet, which is just planet X and planet Y. Finally, in our update function, where we increment the angle of our planet around our sun, we want to call the moon function's update method for each moon around the planet, telling each moon to update its angle around the given planet. This effectively means that as the planets rotate about the sun, the moons rotate about their individual planets. The last thing to do And frankly, the most fun part is let's re-enable our set interval in app.js so that our planets start moving again, and our moons. We uncomment set interval, top and bottom, save our file. Now we have our planets running around the solar system like before, but if you notice, both the Earth and Mars have planets rotating about them. Hopefully, if you were coding along with me, this worked for you also, but I wouldn't be surprised if you did find small errors in your coding. I suggest going back and verifying what you did and compare it to what's in our GitHub repo and make sure you got all the little details correct. We've now reached the end of this JavaScript course. I hope you've enjoyed it, and if you have any questions, problems, or suggestions, feel free to reach out to me at my blog, peterkellner.net/contact.